Hi, thanks for joining me today. I'm going to be evaluating a cool little integral. It's the integral from 0 to pi of 1 over 1 plus cosine squared of x dx. Okay, so there are a couple of different little tricks I'm going to use in order to evaluate this, but if you want to have a go at trying to evaluate this integral yourself, pause the video now and give it a go for yourself, and I'm going to get stuck into a solution. Okay, so firstly what I'm going to do is split this integral into two other integrals first, and then I'm going to simplify it back into one integral. Okay, so this thing here, I'm just going to split it into the integral from 0 to pi over 2 of this thing here, 1 plus cos squared x dx, and then I'm going to do plus the integral from pi over 2 to pi of 1 over 1 plus cos squared x dx. Okay, now that we've got this, what I'm going to do is sort of change this integral here, do a u substitution on it, and then I can bring these two integrals back into one integral. Okay, so the u substitution I'm going to do here is u equals x minus pi. So of course that just means that dx is the same as du, because pi is a constant. Now putting it into this integral here, I get the integral from pi over 2 to pi of 1 over cos squared x, 1 over 1 plus cos squared x dx is equal to, when x is pi, u is going to be equal to pi minus pi, which is 0, and then when x is pi over 2, u is going to be equal to pi over 2 minus pi, which is minus pi over 2. And we're going to have 1 over 1 plus, and now cos of x is now cos of u plus pi, so this is cos squared of u plus pi, and then this thing here is the dx there becomes du. Now, cosine squared of u plus pi, let's just look at what cos of u plus pi is, using our double angle formulae. This is just cos u cos pi, but cos pi is just minus 1. That's minus cos u, then minus sine u sine pi. But remember, sine pi is just 0, so this whole term here vanishes. So cosine of u plus pi is just minus cosine of u, but then when I square both sides, I get that cos squared of u plus pi is just cos squared of u. Okay, so this thing here, I can write as the integral from minus pi over 2 to 0 of 1 over 1 plus cosine squared of u du. And now, of course, u here is just a dummy variable, so I can just swap it out for x, like so. And now we've shown that this integral here, the integral from pi over 2 to pi of 1 over 1 plus cosine squared x dx, is the same as the integral from minus pi over 2 to 0 of 1 over 1 plus cosine squared of x dx. And now I can bring this integral and this integral together to give me this integral and this integral, but then that's just the integral from minus pi over 2 to pi over 2 of 1 over 1 plus cos squared x dx. Now I'm going to use that and work with that integral to evaluate this one here. Okay, so I've just shown that these two integrals are the same. They're sort of exactly the same thing, except the limits here are brought down by pi over 2. Okay, now what I want to do is try and evaluate this integral here. And you'll have with experience that if your integrand has got some sort of trigonometric function, which it does in this case, cosine squared x, generally you want to do some sort of u substitution to get rid of it. Now obviously if this denominator here was 1 minus cosine squared x, we could use the fact that sine squared x plus cosine squared x equals 1, so then this denominator would then be 1 minus cosine squared x, which is sine squared x, but unfortunately we've got a plus sign here and not a minus, so we can't use that identity. And I guess playing about with this, you perhaps will come across this, but what I'm going to write this integral as first is integral from minus pi over 2 to pi over 2, and then I'm going to divide the top and bottom by cosine squared x. So on the top I get 1 over cosine squared x, which is just sec squared x, and on the bottom I get 1 over cosine squared x, which is sec squared x, plus cosine squared x divided by cosine squared x, which is just 1, and then dx is still there. And the reason for this is the top now is sec squared x dx, which we know is an exact derivative of tan x. So if we were to do the u substitution, u equals tan x, then we get that du is equal to sec squared x dx. So this is exactly what we're going to do, and also the fact that we've got pi over 2 and minus pi over 2 in our limits is sort of screaming out to do u equals tan x. So let's bring this integral here. So when x is minus pi over 2, or just a little bit bigger than minus pi over 2, u is equal to tan of minus pi over 2, which is negative infinity. And our numerator becomes, the top limit becomes infinity. When x approaches pi over 2 from underneath, u approaches infinity. Now sec squared dx, as I said, was just du. And on the bottom we have sec squared x plus 1. Now sec squared x is 1 plus tan squared x. So sec squared x is just 1 plus u squared, and then we've also got another plus 1 there. So the denominator is just u squared plus 2, and then du, of course. So now we've shown that this integral here, the integral we're trying to evaluate, equals the integral from negative infinity to infinity of du over u squared plus 2. And now this here is a somewhat standard integral. It's almost inverse tangent of u. We're just going to do sort of a slight tweak, a slight substitution on the u to make this an exact derivative for which we can work out the antiderivative, plug in infinity and minus infinity, and get our solution. Okay, so we've got this integral here now. To evaluate it, I'm just going to try and make the bottom look like u squared plus 1. And the way I'm going to do that is let t equal u over root 2. And the reason for this is, then we'll have that du multiplying through by root 2 gives me root 2 dt. And the reason for this is if I take out a factor of half from the integrand, I can write this then as 1 over 2 times u over root 2 all squared plus 1. Okay, now we've got this integral here. Let's use our u substitution. So this integral is equal to the half, which is out front. The integral from negative infinity to infinity. When u is negative infinity, t is negative infinity over root 2, which is still negative infinity. And the same for the top limit, it's infinity over root 2, which is still infinity. Then du is root 2 dt, and our denominator is t squared plus 1. Okay, we can bring the root 2 out, so we've got root 2 over 2 out the front, which is of course just 1 over root 2. And we've got the integral from negative infinity to infinity of dt over t squared plus 1. This is a nice exact derivative. This is 1 over root 2 times the inverse tangent of t, and that's evaluated from infinity to negative infinity. When we put in t as infinity, we get pi over 2, and when we put in negative infinity, we get minus pi over 2. So we've got pi over 2 minus pi over 2, which is pi over 2 plus pi over 2, which is pi. So this thing here is just 1 over root 2 times pi, which is pi over root 2. I hope you have enjoyed this cool little integral here. We started off with the integral from 0 to pi of 1 over 1 plus cos squared x dx. If you try to do some sort of u substitution straight away, it wouldn't work because there's some sort of discontinuity in tan over pi over 2. And that's why I had to split it into two different integrals, then rewrite that second integral so I can write this integral from minus pi over 2 to pi over 2, so there's no discontinuities in tan in that interval. That means that I can apply my u substitution and carry on with this sort of proof. Do a few u substitutions. This sort of trick is quite standard. If you've got the integral of 1 over u squared plus a squared du, you just sort of take out a factor of 1 over a, and similar sort of thing, do a u substitution, t equals u over a, and yeah, you end up with pi over root 2, so involving pi and the square root of 2 in our solution. I hope you have enjoyed this integral video. If you are new here, please do check out some of my other fun videos, and do consider subscribing if you aren't already. I actually hit 500 subscribers and 600 subscribers as well recently, so I'm quite over the moon about that. So massive thank you if you are subscribed. It really does mean a lot. But as I say, all my milestones, onwards and upwards. Next one, 700 subscribers, I guess. But yeah, I look forward to hitting that milestone and all the future milestones as well. Anyway, I will catch you in the next one. Have a great day.